Sorry, you
Oh,
appear to
yeah.
be on
Yes.
mute.
Okay. Can you hear me now?
Yes.
Yes. And my slides are up. I think it's yes.
Yes.
Okay. Great. Thank you. Hi, I'm Mike Atakita. Thank you for inviting me to give a seminar on dynamic circuits. So, I hope that many of you have heard about dynamic circuits from using Qiskit in our IBM devices in the past. And we actually released our first dynamic circuits capability back in 2022 during the 2022 summit at the end of the year. We released first version of dynamic circuits. But since then, we learned a lot from the first release, and then last year, not even half a year ago, we re-released the utility scale dynamic circuits, and we added a lot of features. So I want to talk about those new features that we've added. But just to start with, I want to talk about what is dynamic circuits. So when I say the word quantum circuits, it's likely that let me just change to the laser pointer. Okay, here. So so many of you have pictured in your mind something like what's on the left-hand side, where I apply a sequence of single and two qubit gates and make terminal measurement at the end. However, on IBM hardware, we have access to a broader set of resources than just unitary gates. So we have components like mid-circuit measurements, classical computation, like classical computation, and even feed forward. So when we take the results of these mid-circuit measurement and feed them into the logic of now classically controlled gates to apply next. So taking this broader set of resources altogether allows us to build dynamic circuits, which are extremely powerful, as unlike static quantum circuits, we can implement any allowed quantum process, not just unitary evolution. And while we know that building dynamic circuits is an essential ingredient for quantum error correction, it is also interesting to ask, can they be used to discover and realize new algorithm and applications along the way? So dynamic circuits are clearly more general than static circuits, but what makes them a promising tool in the near term? So to illustrate this, let's consider the space-time resources needed for quantum circuits. So namely spatial resource, or the number of qubits required, and temporal resources, or depth of the circuits. And dynamic circuits have been shown to be useful in reducing both of these types of resources. So in particular, the ability to reset and reuse qubits can drastically reduce spatial overhead in certain situations. So a simple example of this is in the following staircase circuit, where we apply a sequence of two qubit unitaries and make a terminal measurement. So naively running this circuit requires n qubits. However, we can notice that the left-hand side, each qubit isn't used at all after the staircase until the measurement. So then we might as well move the measurement up as far as possible. And once we do that, we might as well just reset and reuse the qubit for the next staircase. So putting this all together, we see that the result of the left-hand circuit are entirely equivalent to the result of the right, which needs only two qubits, independent of how big the staircase is. And this is just one example of how dynamic circuits can be leveraged to drastically reduce the number of qubits needed to implement quantum circuits with certain structure. However, they are not only helpful for reducing spatial resources, but can additionally reduce temporal resources or depth needed for certain problems. So a great example of this is in preparing a GHD state, which is equal superposition of all zeros and all ones. To make this simple, let's imagine we want to prepare the state on a 1D chain. So if we only have static unitary circuits, the best we can do is the circuit on the left-hand side, which prepares the state by starting from the center and grow the correlation in both directions. With the ladder of CNOT gates. And this circuit requires a depth that is linear in the size of the state. So a bigger GHD state means we need a deeper and deeper circuit. So the reason for this is fundamental. So there is a speed limit for how fast we can unitarily spread correlations. And in this circuit, we are spreading those correlations at a maximal speed along the edge of the light cone. However, with dynamic circuits, we can completely break the speed limit. So in particular, by strategically leveraging mid-circuit measurements, a classical computation, and feed forward, you can prepare a GHD state in constant depth, meaning the depth is completely independent of the size of the GHD state. So a 1,000-qubit GHD state requires the same depth circuit as the 10-qubit one. And the way we do this is with this circuit on the right, which is a bit more difficult to parse. But the high level idea is that we are preparing a lot of little GHD states and then fusing them together with measurements. Then because the measurement outcomes are inherently probabilistic, we apply X-gate to make local correlations on the state conditioned on those outcomes. I'm going to go through an example of how to construct this in Qiskit right after this. But altogether, this ability to reduce circuit depth is one of the most powerful features of dynamic circuits. And it's why we are so excited to bring this new dynamic circuits capabilities to you. So There are already many neat ideas for how these capabilities can be used to explore different applications. These range from preparation of wide varieties of state to realizing certain non-unitary process. And you can even more efficiently compile certain unitary primitives by using non-unitary ingredients. For any dynamic circuits we write down, there's always an equivalent unitary circuit due to the principle of deferred measurement. And for many use cases, dynamic circuits do not appreciably reduce the gate count. Nonetheless, you could imagine using these dynamic circuits capabilities for many applications. So now, here are the new features: parallel ifs, stretch, mid-circuit measure, and a new visualization tool. You can open this QR code would take you to the documentation. And what I want to go through is what we had learned from the initial release of dynamic circuits. In the first release that we had, we learned it was a great tool to start using mid-circuit measurements and doing classical feed forward, but there were some limitations. In particular, if you want to do parallel ifs, you were limited to 10 parallel ifs. Beyond that, by using switch, and then beyond that, you had to do them all sequentially. So the power of dynamic circuits, where you want to make everything constant depth in the quantum part, the classical part actually gets that sequential operation. So now you lose the benefit of having the constant depth. So that was one thing that we learned. And now with the new feature, where you could basically have unlimited number of parallel ifs that you could apply in parallel. And that is why we are calling this utility scale, since if you only have 10 parallel ifs, it's not a large circuit that you could apply. Okay, the second one, what we learned from the previous version is that the unknown delay after the measurement until the conditional operations were applied was limiting with our circuits. There are certain errors that we want to correct during the idling time, such as the phased error that you could apply dynamical decoupling for. So rather than just not doing anything for during that time, we introduce a feature called stretch that actually you could use it for delay instructions for deferred timing resolution. And the third, previously, we only had one type of measure. So you typically would do QC dot measure, and that could be used for either terminal or mid-circuit measurement. But now we have introduced a new class of mid-circuit measure instruction, and that maps to specifically measure 2 that is enabled in a few backends right now. And fourth, without these knowing what exactly happened in the dynamic circuit, it was really hard to debug. So, even by applying mid-circuit measurement, we weren't sure what the scheduled circuit looks like. And then after applying the dynamic circuits, you just don't know how long any of these operations took. So it's hard to figure out where the errors were coming from. So now we have the circuit timing visualization, which is in beta version. So things might change in the future, but this really helps with debugging the circuit that you will be running. So let's go back to the example of GHD state preparation. So in Qiskit, so let's choose n equals 8 GHD. So you could prepare the circuits with Qiskit. In step 1, you prepare these small GHD patches, which are just these 2-qubit bell state. These are these 4 bell states that you see at the bottom. And step 2, you glue the GHD patches by measuring ZZ between edges. So these are the edges that you want to glue together. And then if you look at the circuit, just when you measure these qubits, you want to look at the ZZ. And just for example, if you measure +1, that means that there's no error here. If you measure -1, these states are flipped. If you measure another -1, then again, these are flipped. So for this example, I'm just going to color green, red, red for these 3 measurements. And now you could kind of push them all together. The light blue shaded ones are the ancilla qubits that's been measured, but it is part of the GHD state. And now, first, you want to re-entangle the measured qubits. So these are ancilla, so you don't have to re-entangle, but by re-entangling, you are just creating a larger GHD state. So you re-entangle the measured qubit, and now you see that all these, the bits have been flipped, depending on what the outcome was. And now, by looking at where these green and red boundaries are, you could start applying these corrections. So you hit the green wall. Okay, this parity would flip these 2 qubits, this condition to X, and this red, the second one, the parity between green and red is what flips these. So now the parity between these 2 is 1. So now you want to flip these 2 qubits, these 2 qubits. And then now for the last one, you look at the 3 parity, the parity of these 3, and now there are even number of red, so you just leave it alone. So that makes it into all 0 and all 1 GHD states. I hope that wasn't too confusing, but this you can kind of imagine this example. There were three parallel ifs. So you could have written this in the previous version of the dynamic circuits using switch statement to run these operations in parallel. But imagine if you want to generate 120 qubit GHZ state, you need about 50, at most 59 or 60 mid-circuit measurements and apply that many ifs. And that would have taken forever to do this in the previous version. So this new feature, such as this parallel ifs, helps circuits such as GHZ state preparation. Now, I want to use this tutorial that I have, the long-range entanglement, to add to discuss the new features that we have added so far. So long-range entanglement between distant qubit is challenging on devices with limited connectivity, but this tutorial shows how dynamic circuits can generate such entanglement by implementing a long-range CNOT gate using a measurement-based protocol. So following this Elisa Baumer's paper, the method uses mid-circuit measurement and feed-forward to achieve constant depth gates, regardless of qubit separation. Right, so it creates intermediate Bell's pairs and measure 1 qubit from each pair and applies classical condition gates to propagate entanglement across the device. So this avoids long swap chains that's needed with unitary circuits. Okay, so this is just, let's generate a Bell pair across the long distance. So imagine that you don't have access, the direct CNOT axis on this device. If it's a linear device, a nearest neighbor, limited connected device. And on these examples, I'm going to refer to distance as how many qubits you have in between the control and the target qubit. So this example would have distance 2. And this Bell pair, you could use swap gates to prepare this Bell pair. So now if you grow in distance, for example, distance 4, now the swap overhead, it grows and grows. So the 2 qubit gate layers gets larger and larger. And then at distance 6, you see how quickly the depth increases when you increase the distance. So now let's consider long-range Bell pair using gate teleportation. So now with the same distance to Bell pair, this is the same Hadamard Bell pair, you generate a Bell pair in the middle. And then this is the CNOT teleportation part. You measure these qubits, and the Z measured qubit applies a Z correction by applying an X flip, and then this X measurement corrects for X errors, correct for X's, and by applying a Z. Right, so when you grow the distance, you see that you now are generating more Bell pairs. If you go to distance 6, you're going to have another set of Bell pairs, but it's going to be the same way. So it's going to be a constant depth. Every time you grow in distance, you're only growing the number of 2 qubit gates, but you're not growing the layer of 2 qubit gates. But now there are more measurements. What do you do with it? You look at first the Z measurements, you look at the parity and apply a Z correction by applying an X. And then also for here, you do X basis measurements and look at the parity and apply X correction by applying a Z. So this is exactly the same throughout any distance. So looking at this circuit, we talked about how single qubits, 2 qubits measurements, these are defined duration, but after you measure, you don't know how long it actually would take to get those measurements to the place where they could do the calculation and do the classical operation and apply this feed forward. Right? So these duration could depend on how many measurements you have, how complex these classical operations are. There's a lot of things that goes in, but to us as users, we just don't know. So I will come back to this point when I describe the stretch feature. But first, I want to talk about the quality metric for Bell state. So I chose the fidelity of the Bell state to be this form. So the circuit that I described earlier is just initialize the control qubit, prepare Bell pair, and measure neighbor qubit pairs, and apply the feed-forward correction. So you just apply these steps, and then before the final measurement, you apply gates to either measuring X, Y, or X, X, Y, Y, or Z, Z. So for one distance, I run 3 circuits and get the fidelity for each point. So now on this plot is showing the Bell state fidelity versus the distance. So I just took this data yesterday on IBM Boston, and the blue curve is the unitary curve. So as you grow in distance, you see the fidelity going down, right? This is expected as you grow the size, you are applying more and more and more in swap gates. So there are more 2 qubit gates, and the depth is much larger. But now with dynamic circuits, maybe in the smaller distance, it's very similar, or maybe it's a little worse than the unitary case, but it doesn't go down as quickly as the unitary case. So with the dynamic circuits, we still have as many 2 qubit gates, or not as many, but there are a lot of 2 qubit gates. It's just that they're all constant depth. So we are reducing the error that's coming from the time. But it's nice to see that there's some crossover. And then towards the larger distance, the dynamic circuits approach of applying this long range C naught is doing better than the unitary case. So this circuit I ran from just out from the notebook. I didn't apply anything. I didn't apply DD. I didn't apply do any tricks to running this. I also just selected the string of qubits that was provided as the best string on the back end. So it's pretty simple. You could check all these out from the notebook. But first, I want to start by adding dynamical decoupling. So in the unitary case, it's pretty straightforward. You could use the typical transpilation pass and the dynamical decoupling pass that is available. And the DD pass that I used was a quarter delay, a pi pulse, half a delay, and then a XM, and then another quarter delay. So I applied this on the unitary circuit, and you see slight improvement, especially on the larger distance. So you could see that, in the shorter distance, it's still quite dense, the two qubit gates, but as you go longer and longer, there's a lot of empty space. So these DD sequence does seem to help with the fidelity for when the depth is much larger. So now, can we do the same thing for dynamic circuits? The answer is no, because we talked about how the delays are unknown. So all these delays are what we just don't know when we are writing the circuits before running the circuit. But now we could use this new stretch feature as a duration for delay instructions for different timing resolution. So the example of this is rather than now it's a question mark, you just assign a stretch, right? So now you have a stretch pi, stretch twice, and then XM, and then another stretch. So here you see the code snippet where you could write something like this with add stretch DD, define the stretch, delay, pi, delay, these pulse again, and then another delay using this stretch. In the notebook, the LRCX is how we were generating these circuits for each point. You could insert this block into the notebook by using this add stretch functionality. And for this example, I just add the stretch DD on the control and target because all the middle qubits are just being measured and not used afterwards. So after the measure belt basis, I add this stretch onto the control qubit and the target qubit, and then finally do the feed-forward application. So by doing this, now you see the one that I added, the stretch DD, is in pink. So again, similarly compared to red, it brings up the curve a little higher, and it also smooths this out. So these are very nice to see that the stretch DD is working, and also the DD in the typical unitary case is also working pretty well. So the plot is getting a little crowded, so I'm just going to remove all the non-DD cases and want to introduce you to another feature, which is a mid-circuit measurement feature. So I mentioned before we only had one type of measurement, which is just the measure instruction, but now we have mid-circuit measure, which maps to measure 2. So the measure 2 today, we have rolled it out to several backends, and it's typically faster than the typical terminal measurement. So this is just a code that I took from the documentation on the measure qubits documentation. You could import mid-circuit measure, and rather than applying this, circ.measure that you would typically do, you could do circ.append the mid-circuit measurement, right? And then when you look at it, now the measurement instruction, you could see this block where it's the measure on qubit 0, and then putting on the classical registry 0. So I replaced all the mid-circuit measurements with measure 2 and rerun the circuit. And this one also, I added the stretch DD. And see, there's another slight improvement going from pink to the yellow color. So you see that this measure 2, by having this faster measurement for mid-circuit measurement, is indeed helping with these dynamic circuits operations. And okay, so finally, this is the last feature. But this is, even though this is in beta form, it is extremely helpful if you are actually running the experiments and if you actually want to visualize and debug, try to figure out what is actually going on in the circuit. So again, there is a documentation here, visualize circuit timing. And I just took a screenshot of that page again. So you can see that the thing to note is that before you submit the job, you do need to add an extra option in the sampler option to get the scheduled timing to come back. So this is set to false as a default. So after you run, if you don't set this up, you won't be able to retrieve the information in the metadata. So make sure if you're actually running an experiment on real back end, you tell this to say set it to true. So then at the end, when you get the job result, you could get this information from the metadata. So there is a circuit scheduled timing that you could pull for visualization. And in the documentation, I was looking at it yesterday and I didn't notice, but this was not part of the documentation, but there is something called circuit duration. So this is also very useful this just tells you for each circuit how long the circuit is from the very beginning of initialization step to the very end of the measurement step. So I'm going to use this circuit duration to plot out how different these circuits look along the distance. So here is a plot of circuit duration in microsecond versus the distance. So let's go from cyan at 0. This is just a single 2 qubit gate, a Hadamard single 2 qubit gate, and then a measurement. There's a lot of it's the number here is pretty large because this timing includes the initialization that is prepended to your circuit. But nonetheless, this should be close to very, very fast. But as you see, as you grow in the distance, the duration is linearly grows because you just have more and more swap gates. So now, if you compare the pink versus the yellow, this is the difference that is coming from the mid-circuit measurement duration. So just by reducing the duration of the measurement, you see improvement in the duration. And it's really nice to see that initially, when you go to the first distance, distance 1, you add a mid-circuit measurement. Mid-circuit measurement is quite much longer than the 2 qubit gate, but it just gives us a bump first, and then it's a lot flatter than how quickly the unitary gate is increasing the duration. So again, as you increase in distance, you have many more qubits that you're measuring, and you also increase the complexity of the classical operation that you're running. So it is expected that the duration will be, it's not exactly constant for adding more ifs, but it's much slower slope. In the previous version, if you had done this sequentially, okay, so actually this is only 2 ifs, but it would always, for like GSG example, you would just see this grow so fast. Okay. Now, okay, I think I'm taking up a lot of time, so let me just really quickly go through. This is again from this documentation. I just want to add that this is the way you could draw the circuit from the metadata that you retrieve. And the only thing that I changed is include channel instead of none. I specifically added the qubits used so that I only draw out the qubits that I use. This is kind of like the idle wire false setting that you might be familiar with in the draw setting, right? Okay, so let's go back to the distance 6 example. This is the unitary with the swaps. When you look at the metadata, now here are the 2 blues in initialization, and greens are the 2 qubit gates. So you could see this X kind of structure similar to what you would normally imagine from the Qiskit drawing. And the purple is the measurement. So you see, you could imagine as you grow in distance, this X gets larger and the duration gets longer and longer. So now with the DD, you see there are a bunch more pi pulses. So you could see these more lines inserted where these blanks are. Okay, now dynamic circuits. Now, sorry, the color has changed, but now the purple is the 2 qubit gate and orange is the measurement. So there are 2 layers, a couple layers of 2 qubit gates, a mid-circuit measurement, and this is the time that we just don't know how long it would take for these operations. And then finally, some gates that's applied to the control and target, and then the terminal measurement on the 2. But as you see, all the 2 qubit gates are running in the same constant depth. So you could imagine as you increase in distance, it's still going to be the constant. So now using measure 2, now the first mid-circuit measure is much shorter. So you see how much reduction in the delay that you got just by reducing the measurement pulse. And finally, with measure 2 and stretch DD. So now I didn't know how long this duration was, but by using stretch and then the 2 times stretch and the stretch again and applying these pulses, you are actually applying the dynamic decoupling sequence as I had hoped. So all these features, you could see the improvement from measure 2 and the stretch DD and visualizing the circuit duration and also how the circuit was scheduled at the end. These are all the new tools that we have added in the last year with the new release of utility scale dynamic circuits. And I really hope this seminar kind of gave you an idea of why we are calling it utility scale dynamic circuits and why we're very excited to, even though the first release was from 3 years ago, I'm very, very excited to use these new features. And I think we have a lot more areas of experimental implementation that we could do using these new features. So check out this QR code and just make sure to go to the very bottom of the documentation. That's where you could find links to specifically for stretch, mid-circuit measurement, and the visualization tutorial. Not tutorial, sorry, the documentation. Okay, thank you.
Thank you so much, Micah, for that excellent presentation. And it looks like our advocates are also pretty excited about these features. Now I'm going to be pulling Ian up into the stage.